All right, hello. So this is the third video of section 2.2, and like I had promised before, we're going to go over exactly how you find the inverse for a matrix in higher dimension than just a 2x2 matrix. So remember what the theorem last video told us was that if this matrix A is invertible, then it should be able to row reduce to the identity matrix, and the same sequence of row reduction steps that I used to transform this into the identity will transform the identity into A inverse. So in order to calculate the inverse, we should always start by trying to row reduce this matrix into the identity. But it would be a lot of work to do all of these row reduction steps and then start over and do all of the row reduction steps again, even though I know what they are. So why not just do the row reducing of both matrices at the same time? So what we're going to do to find the inverse is we're going to set up this special matrix where I sort of partition it so that on the right I have A, and on the left, I have the identity matrix I3. So the 3 by 3 identity matrix on the left and A on the right, and A on the left. And so what I'm going to do is I'm going to row reduce this side again to the identity, if possible, while doing the exact same row operations on this. And so in that way, I can save time because I will be doing both calculations at once. And so what will happen is I'll try to row reduce this to the identity. If at any point I figure out that I can't, we will stop and declare A not invertible. But if this reduces all the way to the identity, then the matrix we wind up with on the right here will actually be the inverse of A. So let's do some row reducing. So if I'm going to row reduce A, the first thing I want to do is calculate 3R1 plus R2. And so notice in particular that I did the exact same thing on the identity matrix on the right here. So I did 3R1 plus R2 on A for the purposes of row reducing A and on the identity matrix. And so that's why we wind up with the two matrices we wind up with here. And so now I'm just going to go about the row reduction algorithm, making sure to carefully do the same row steps on this matrix each time. So now I want to do negative 2R1 plus R3 to A. So negative 2R1 plus R3. Negative 2 times 2 is 4, plus 4 is 8. Let's see, this should be a negative 3. Yep, so doing that. And now the identity, 1, 0, 0. 3, 1, 0. And so since I did negative 2R1 plus R3, I'll get a negative 2, 0, 1 here. All right, so next up, I want to clear this negative 3, so I'm going to do 3R2 plus R3. All right, so 3 times 3 is 9, so I get a 7 there. I get a 3 there, and I get a 1 there. All right, so I'm actually almost done with this. So I, again, sort of you get to choose a little bit the order that you do these steps in. I noticed that this 2 is easily going to clear out these 2's above it. So before turning that 2 into a leading 1, I'm going to first do R3 plus R2. And so here I have to do R3 plus R2, so that's 10, 4, 1, 7, 3, 1. And then I'm going to do R3 plus R1. And so here I should get 8, 3, 1, 10, 4, 1, 7, 3, 1. And now I want to finish with 1/2 R3. And so notice I've transformed the matrix, which was A, into the identity matrix. And I'm left with this new matrix on the left, which, assuming I did everything right, should be A inverse. And so that's how we do it. So you just sort of set up this special sort of augmented matrix where I'm sort of augmenting by the identity, and then we just row reduce. And so, again, if A is invertible, we'll wind up with something like this, where I, sort of move the identity over to the left in a sense, where I transform A into the identity on the left, and then I'm left with A inverse on the right. With that out of the way, let's do one more example, and then I'm going to end with just a few facts about invertible matrices. And so on the worksheet, you'll have 2 examples, one where you'll show a matrix is invertible, and one where you will show a matrix is not invertible. So they'll sort of mirror the 2 examples. So I guess I've sort of given away the punchline here is that we're going to show that this matrix is not invertible. But what I like to do, so we'll pretend for a moment that we didn't know, because what I like to do when asked to find the inverse of a matrix is, if possible, so often you'll get a question asking, and so actually I'll phrase this question in a way that would be one that you might see commonly. So you might get the question, if possible, so we'll define this. We'll say let B be the following matrix, and then if possible, calculate B inverse. And so often you'll be presented with a matrix and you won't know whether or not its inverse actually exists. And so what I like to do in that case is just set it up like I'm going to find the inverse. And so what I mean by that is I'll just start by setting up this special matrix here, and start row reducing and act like I'm going to find the inverse. But then once I get to the point where I can't, I'll stop. So what we're going to do is pretend I haven't already given away the fact that this matrix will not be invertible. We're going to try to row reduce this. So we'll do the algorithm again. All right, so doing the row reduction algorithm, we want to do -4 R1 plus R2. So I get a 0 there. I get a 1 there, and I should get a -1 here. And -2, 6, -4. All right, so here 1, 0, 0, -4, 1, 0, 0, 0, 1. So I'm just proceeding as normal. And next I'll do 2r1 plus r3. (0, 2, -2), and 1, 0, 0, -4, 1, 0, 2, 1, 0, oh, 2, 0, 1, sorry. And so now I can already kind of see that I'm going to get a row of all zeros, which will sort of end the process for us. So we're going to do -2 r2 plus r3. And so notice at this step, this row of all zeros implies that A cannot row reduce to the A identity matrix. So A is not row equivalent to the identity matrix. And so therefore, I'd actually just end this by saying A is not invertible. And so this will be the general sort of tip-off for knowing that A cannot row reduce to the identity matrix, is that you're going to get a row of all zeros. That is, you'll get some row that does not contain a pivot. And so yeah, it's because A is a square matrix that we can sort of guarantee that A not being invertible gives us this row of all zeros. That sort of ends my examples for invertible and non-invertible matrices. So like I said, I just want to end with 3 facts about matrix inverses in general. And we'll shortly, or give very brief proofs, I think, for each of these facts. And so on your worksheet then, you should be able to show that A is invertible and that B is not invertible, much in the same way that I just did with these 2 matrices. All right, so let A and B be 2 invertible n by n matrices. And so we want to state 3.5 facts, actually. I'll show you what I mean by half a fact in a second. So first off, I claim that the inverse of A inverse is equal to A. Why is that? Well, so to observe this fact, all we need to do is think about the definition of what it means to be the inverse of a matrix. So remember, the fact that A and A inverses are inverses of each other means that their product is equal to I sub n. Well, so in the definition of A being invertible and what the inverse of A is, the definition of the inverse is just the matrix who, when multiplied, gives me the identity. So all we need to do to show that this is true is just swap the roles of A and A inverse in this equation. So in a sense, make A inverse the main character of this story. Well, then A is the matrix who, when multiplied by A inverse, gives me the identity. And so this is where this relation comes from. And so in that way, the inverse can sort of cancel itself out, right? So take the inverse twice, and you'll wind up in the same place you started. All right, so fact number 2 And this one is going to be the fact that actually gives us another half of a fact. A times B inverse. Well, so if A and B are both invertible, then the product of the inverses behaves much in the same way that the product of the transposes behaved. So that is A times B inverse, so the inverse of this matrix, A times B, is equal to the matrix B inverse times A inverse. So to see this, again, we just need to check that A times B times B inverse A inverse is equal to the identity matrix. Well, this is equal to the following. But B and B inverse cancel each other out to leave me with A times A inverse, which cancel each other out to leave me with the identity matrix. So you can sort of see, I think looking at this, you can sort of see why this works, that you take the inverses, or you take the matrices, flip them around and calculate the inverses, and then they sort of one by one cancel each other out until we're left with just the original, well, the identity matrix. All right, so one more fact and then one more half a fact. So the inverse of the transpose, so A transpose inverse, is equal to the transpose of the inverse. And so that is, these two operations, A inverse and A transpose, can sort of flip around. That if I had to calculate them both, I could calculate them both in any order, and I'd get the same thing either way. Why is this? So to see this fact, I want to first look at the transpose of A times A inverse. So we know that A times A inverse is the identity already, and so keep that in mind. Also keep in mind that if you think about the identity matrix, right, it's a matrix with only ones on the diagonal and zeros everywhere else. And so the transpose of the identity is actually just the identity. So here, and maybe I'll put it sort of underneath, this is just the identity. So this is secretly the identity. It's just a very confusing way of writing the identity, I guess. So notice, remember, the transpose works in the same way that the inverse works. So if I want to distribute this transpose in a sense, I can take it through and then just swap the order of this product. Well, if I wanted the inverse of A transpose, I've actually found it. Because remember, as we've stated, this is equal to the identity. And so this shows that the transpose, the inverse of the transpose is equal to the transpose of the inverse. All right, so very briefly, I want to state fact 2.5. Actually, I'm going to, so I'll erase fact 3 here and then state fact 2.5. So fact 2.5, suppose I have just a lot of matrices which are all invertible. So suppose all of these matrices are invertible and they're all n by n matrices. Well, so I claim we can actually take the same idea from fact 2 and apply it to this arbitrary amount of matrices. So that is, if I take the product of all of these matrices, its inverse should be the product of the flipped, well, of the inverses, but with the order flipped. And so to see this fact, notice that all I have to do again is check, well, let's do A1 times A2 times AP. So this is the original product times AP inverse, AP minus 1 inverse, and so on. Well, so notice the same thing that happened here, where the inner matrices canceled each other out sequentially, is going to happen here. So first things first, AP and AP inverse are going to cancel each other out. Then AP minus 1 and AP minus 1 inverse will cancel each other out. And these matrices will just keep canceling each other out until we're left with the identity. And so in this way, we can apply this logic for fact 2 to the product of an arbitrary number of inverses to give us fact 2.5. So that will wrap up this section. And so next we will go into section 2.3 and 2.4, both on Wednesday.